interests include security and privacy, pervasive computing for healthcare, and wireless networks. He has published over 175 refereed journals and conference papers and obtained over $66 million of grant funding. He's a fellow of the IEEE, a distinguished member of the ACM, and a 2008 Fulbright Fellow to India, and an elected member of Phi Beta Kappa. After receiving his AB in computer science and physics from Dartmouth in 1986, he completed his PhD in computer science from Duke University in 1991 and returned to Dartmouth to join the faculty. So the stage is yours.
Thank you. It's great to be back in Bangalore. As he mentioned, I was a Fulbright scholar in India.
I have one more thing. So he was also one of the co-chairs of NetHealth long back, and also he changed comms. So it's nice to have you back.
Yes, well, in fact, during the CommsNet's 2009, we founded NetHealth, and it was so it's lovely to see it thriving, and to be back in Bangalore, where I spent the year as a Fulbright scholar at IASC. It's one of my favorite places to be. And so today I wanted to talk about some of the work that we've done over the last 5 years in a group focused on a project called Amulet. And Amulet is really derived directly from my work at IASC, which is where and when I began my work in mobile health and networked health. So to begin with, I want to just make sure you understand what I mean when I say mHealth, because it's one of those buzzwords that has so many meanings it almost has no meaning. My meaning is very broad. It's the use of mobile computing and communications technology, either for the delivery of healthcare or the collection of health information. Everything from clinical use of health technology to remote patient monitoring or rural healthcare or public health monitoring. All of those things fit into my sense of mobile health. Now, in the years since then, it's been almost 10 years, lots of applications and devices and technologies have come out, and we're all familiar with them. Many of them are personal or wearable technologies, but some of them are shared kinds of technologies. You might have a scale that's shared by everyone in a household, where you might have not health-specific, but still useful, meaningful information like humidity, temperature, air quality sensors you might have in a home or an office or a city, all of which are useful data for mHealth applications. This work in our project is focused on wrist-worn technology, which is sort of typified by two extremes. On the one hand, fitness bands that are purpose-specific, designed specifically for fitness applications, tracking your steps and so forth. And the other extreme is a smartwatch, which is a more powerful platform, maybe runs multiple applications, but tends to have maybe a one-day battery life. And so the problem that we have noticed with these is that they typically are closed platforms. Maybe you can write apps for them, but you certainly can't get inside and hack away with the operating system or the underlying hardware. And in our group, we wanted to explore security and power efficiency at the lowest levels, and so none of these platforms were suitable for us. We also wanted mobile health applications that were for critical uses that might last for days, weeks, or even months without needing a recharge. And so our project aimed at developing ultra-low power, very secure platform, which we call Amulet. And this is a word that I like because it sort of evokes a sense of safety and protection, which, given our security focus, is important. And so here's kind of the big picture of the Amulet system. Here's the person or patient down here who is wearing an amulet and wearing perhaps some other health-related devices, measuring physiology or behavior. And that information is all collected by the amulet. So the amulet is kind of a smart hub for the mobile health information. And when the smartphone is available, that information can be pushed up to the cloud for storage or analysis or sharing. And I say when the smartphone is available because the phone is not always physically present. Maybe it is for you and for some of the younger generation. In my case, I tend to have the smartphone is not always with me. The microphone, it seems. So I'm going to continue, and maybe they'll figure it out. But this is not working. All right, I'm going to go. So the reason we wanted to design a platform that would last for weeks is that it was necessary sometimes for continuous data collection, even in the situation where the smartphone was not present. Now, this cloud is also a source of applications, and we envision a future in which a physician might actually prescribe apps, and that is starting to happen now, where people are using applications prescribed by their physician or their coach or their wellness coordinator or something like that. And so we want to have a platform that has multiple applications, like a smartwatch, very strong security, very long battery lifetime, and developer tools that can help developers achieve those goals. So this is what Amulet looks like. And I actually brought one here. I'll pass it around. It's running a test application. It's not very interesting right now, but if you push the lower left button, it'll switch between different apps, a clock and various other sort of system test applications. This is what it looks like inside. And one of the ways we get to do all the kinds of low-level research is we developed our own hardware. So it's a custom board, custom operating system, custom compiler, custom runtime system, custom applications, and custom development environment, all custom. So it has some sensors inside it, a gyroscope, 2 accelerometers, an ambient light sensor, a UV light sensor, a temperature sensor, a microphone for sound sensing, and of course sensing the battery level so we can manage power. 2 microcontrollers. One is an M0 focused on the BLE, the Bluetooth, and the other is an MSP430, a very typical standard ultra-low power, very simple platform, and a micro SD card, so you can store up to 2 gigabytes of health data. It does have BLE, as I mentioned, and we use that so that the Amulet is a hub of local devices, a heart rate monitor, for example, or I'll show a couple of others that we've developed. And the same BLE can be used to talk to the smartphone. It has this very simple display. It's something like e-ink. It uses no power unless you change it. And so it's very simple. It's black and white, only 128 by 128. But as you'll see when you look at it, it's sufficient for simple applications. It has a couple of LEDs, one red, one green, for simple output power and that sort of thing. And it has a buzzer. You'll see in one of the apps is just a buzzer tester. That's good for notifying the person, maybe they should pay attention and see some new information. It has 2 buttons on the side. The bottom one is for switching apps. The top one is app dependent, whatever the app wants to use it for. And then this piece here is actually a capacitive touch slider. So unlike today's touch screens, which are very power hungry, this allows you to just sort of scroll through menus and other simple interactions like that. So we've developed a range of applications, and I'll talk about some of these in more depth and others I don't have time for. For example, we have a group at Dartmouth very interested in stress and the ability of monitoring someone's stress so that you can use that as an indicator, for example, of their likelihood of using drugs. We have a whole group interested in the abuse of smoking and illicit drugs, and if you understand people's stress, you might be able to intervene and help them avoid that behavior. Heart rate, a very simple heart rate monitoring app that just records your heart rate over time using an external wireless sensor. Typical activity monitoring, for example, how many steps or how much time you spend in physical activity. An activity encouragement application, sort of, okay, you've made half of your goal today, please keep going. And I'll talk a bit more about this TheraBand sensor. And there's a fall detector, it's a pretty typical application, a sun exposure, and also EMA, ecological momentary assessment, a standard method in measuring lifestyle. So you prompt the person to answer questions every so often. All of these are built on top of Amulet OS, the operating system, which is a custom combination of simple software with an API. Applications are written as state machines. So as a developer, you just define a set of states, a set of events that transition from one state to another, and what happens when that event occurs. So if someone pushes a button, what should you do? When you receive new sensor data, what should you do? And then the app can call APIs for logging data to the SD card, or setting timers, or encrypting data, checking the power level, displaying something, etc. One of the key goals was to make sure that the system is secure so that an application that's buggy or malicious cannot affect other applications and cannot affect the operating system. This is standard practice, of course, in today's operating systems, but this microcontroller is incredibly simple, doesn't have the hardware to support that level of protection. And so we had to develop a tool chain to compile applications from C into a set of applications that run as a firmware image. And that means that we had to translate the application into this underlying platform and block potential misbehavior. So the first step is to analyze the C code and reject any use of inline assembly, go-to statements, recursive function calls, and other things that could perhaps lead to problems. And then to insert code to do bounds checking on arrays or check the pointers to make sure that your accesses to memory stay within your application's memory area. We do use the memory protection unit, the MPU, that is provided on the microcontroller. Very primitive, but it does provide some hardware support for memory protection. The other thing we needed was tools for the developer. So if you want your app to run for a long time, or more to the point, a combination of applications to run for a long time without recharging, you need to be able to predict how much energy is used. So we have this nice graphical tool that shows the state machine that your program is using, and then you annotate how often do each of these events happen according to your expectations. And then it will automatically compute how much time it will, how much time the battery will last based on that. So that is built on an analysis of the code and a pre-computed profile of the device. In other words, how much energy does each instruction use? How much energy does it use when you use the network or write to the SD card? And a very simple model that kind of combines all that information to predict the energy usage of an app or of a combination of apps. And we were then able to use this or evaluate this really by writing a combination of apps and then running them and monitor their energy use. And you can see here for a variety of applications the amount of power consumed. So a smaller bar is better. And we've annotated each with the number of days that we anticipate the amulet would last if it were running only that one application. Even the most power hungry, which is using the network and the SD card to monitor your heart rate constantly, would last for 2 weeks. And so we're pretty pleased with that. Some of these, like just running the clock, might last for a better part of a year. But how well does our predictor, how well does our model actually predict that level of performance? And so I'm not going to go through all the details, but we get about 90 to 98% accuracy in predicting the battery lifetime using that model, which is close enough probably for most purposes. So we've used the amulet since then, since developing it, for a lot of different research. Many of these you'll see correlate with the applications I mentioned earlier. Some of them are more sort of systems-oriented, sort of security and memory protection. Some of them are the human factors, and I'll talk a little bit about each of these. So we've done 4 stress studies. We're actually right in the middle of the 4th one now. Each one has been a little bit more sophisticated, a little bit more in the terms of number of subjects, but in our previous study, which was completed, we had 26 participants, and we brought them into the lab, put the amulet on them, put a heart rate monitor on them, this polar standard commercial heart rate monitor, and then stress them out. So we actually do things to the person that causes stress. These are well-known tests that are used for stress studies, very, non-harmful, right? You put their hand in ice water, or you startle them by making a sudden noise, and then we send them out for 3 days into their normal activity, and we monitor their heart rate, and the amulet is running, and we ask them occasionally, how stressed are you? And we use that as the sort of ground truth and compare that with what we can infer from the sensor data. And the bottom line is that we were able to get a reasonably good accuracy. F1 is an accuracy metric of 0.81 out of 1, 80% roughly accuracy on our inferences of stress. We want to do better, and we're repeating it now with better sensors, better algorithms, and adding a new EDA sensor. EDA is electrodermal activity, otherwise known as GSR, galvanic skin response. And we wanted to be able to measure that because the sweatiness of your skin is one measure of stress. And so we didn't find one that was readily available that would measure that and send the data in Bluetooth form and would run for days. And so one of our students developed this wearable wristband, which has 2 electrodes on it for measuring the resistance of your skin, and a small microcontroller-based chip or board to collect that information and record it in memory. Another project was driven by the interest of a physician who works with older adults, in particular with obese older adults. These people living at home need to retain enough strength and physical mobility to stay at home and to stay active doing their normal activities. And so they typically are asked to do some sort of exercises. This is a TheraBand. That's a brand of resistance band that is used for simple kinds of activities that help people maintain their physical strength. So his goal is not to help them reduce their weight, but just simply stay sufficiently strong so that they can stand up, sit down, go to the theater, whatever. And what he wanted was to say, how often are they using their TheraBand to do their exercises? How many repetitions do they do? How hard are they pulling? And are they doing them correctly? And there was no way of measuring this. And so our students developed a sensor that is really just between the handle and the stretchy band. It's a pressure sensor and a small Arduino microcontroller-based system to collect that information and transmit it to the amulet. And then the amulet, of course, can use that information to measure and count repetitions or what have you. This is what it looks like all together. So it's a standard handle and the resistance band. There's the sensor is in here in this handle, and then there's a case, 3D printed case for the BLE Nano. That physician also wanted to monitor how active were those adults. So how much time did they spend in low sedentary activity, walking and sort of moderate activity, or maybe strenuous activity, and eventually then prompt them to be more active. And so we started by just a monitoring application. How accurately can we measure low, medium, and stressful or strenuous activity? And then we modified that application to actually provide prompts throughout the day. And we have a couple of studies showing reasonable accuracy and that the adults, even older adults, found the applications usable. We have a whole group within the Amulet project who's focused on the human aspects of this, the design and the interfaces and how well people can use them and what people would want out of such applications or devices. And the first thing they did was to develop a list of 20 design considerations. So if you're developing an app or a device for older adults, or for that matter, for anyone, what are the kinds of things you should think about? And these are in alphabetical order, but obviously everything from aesthetics. Does it look nice? Is it comfortable, right? Does it, scratchy or something like that? And, is it protecting my privacy? In fact, we asked them specifically about privacy, whether they were aware of the risks of collecting and sharing and using this kind of personal information through wearables, and how much they cared about that, and what degree they might want to control the sharing of their data. In fact, one of my students was specifically interested in that sharing. What's the point of collecting all this information if you never share it? And in many cases, you want to share it with your clinician or with a family caregiver, or if you're an athlete, as she was, with her coach, who's monitoring and helping her improve her athletic performance. And so she developed a cloud-based system in which the Amulet would upload data through the smartphone to the cloud in encrypted form, so no one could read it, unless you had previously given them the relevant keys. And what was interesting about this was that I think for the first time, it was really a way of sharing a stream of data with cryptographic controls. So the user can select what subset of the data a particular person can decrypt, and what subsequence, which days or which weeks that person should be allowed to access. And then very easily, prepare that. So her focus wasn't on the interface, but more on the cryptography. All of that was about research, but the Amulet, I think, is also useful for educational purposes. You could use it in a course on wearable computing. Obviously, you could have the students doing either app development or maybe lower level systems development. If you wanted to teach embedded systems, this is an embedded system and you could get inside it. It's all open source, open hardware, so they can study what we have or modify it. In digital electronics, of course, they can modify the board and produce new or different versions. And perhaps I think most interesting would be a cross-disciplinary course. Bring together electrical engineers, computer scientists, physicians, or health professionals to actually co-design some interesting applications, which is in some ways what we've been doing in our work with physicians. And ultimately, students in a design course could critique our design. I'm sure it's not perfect, or come up with a better design. Everything from the 3D case, or whether the buttons are on the same side or opposite sides, whether the buttons are on the right side, the left side, where the cap touch slider is. We spent a lot of time on that. We made some mistakes, and that would be interesting, I think, as an educational process as well. So this is the amulet. Hopefully it's still going around, and we've recently produced 150 of them. They cost just a couple $100, even in small quantities like that. It's secure, it runs multiple applications, it's open hardware, open software, so you can download it yourself. It has good battery lifetime, and we have developer tools to help predict that lifetime. And this is where you can find more information, amuletproject.org. And through that, you can both download our papers and also reach the GitHub, where you can download all of the information. So I'm the name on this paper and on this talk, but believe me, there are tons of people who worked on this project, who did all the real work. And since it's been going for about 7-8 years, over time, there have been a lot of students involved, undergraduates, graduates, postdocs, faculty from both Dartmouth and Clemson. This just happens to be who was there at our most recent meeting last summer, but there's a lot of great people. It was funded by the National Science Foundation and the Department of Health and Human Services, and again, this is the website where you can get everything. So with that, I'm happy to take questions. Thank you. Yes, please.
What is the sampling rate you are getting for the sensors?
I'm sorry?
What is the sampling rate you are getting?
The question is, what is the sampling rate?
Yes.
You can choose as a developer, and it depends on the sensor. An accelerometer may be 200 hertz, but a temperature sensor may be 1 hertz.
Okay. And for, are we able to track all the 24 hours data? We can save it?
Yes, you can track for 24, 48, 72 hours and save it to the SD card. That's what we do, typically.
Okay.
You don't have to, right? You can consume the data and use it in real time for some application, or you can write it to the SD card, or you could submit it through Bluetooth.
Okay. Is that device is open to all? Means can we procure it or?
Yes, yeah. It's all on GitHub, so you can download the software, and you can download the hardware specifications and manufacture your own.
Okay.
I have 150. We're using some of them in our own experiments. I could probably share a few if you wanted them.
Okay. Thank you, sir.
Sure.
Any other questions? Okay, let's thank Professor Coates. I request Rajiv, who is part of steering committee of CommsNet since inception, and also call up Rohan to give the memento to Professor Coates.
Okay. Dave, thank you so much.
Yes.
Wonderful talk. Sorry I was late. It's always a pleasure to hear Dave, known him for a long time. It's greatly appreciated.
Thank you.
Thanks.
Good to be here.
Been a stellar support behind the company. Thanks, Dave.
So next we have paper presentations again. So we have fabrication of microfluidics impedance cytometer for leukocytes analysis by Prakhar Jain from MicroX Lab. Okay, Usama Abbasi from MicroX Labs, India.
Not working. I don't know. Who is responsible for this?
you know. So we are a microX lab team, and we are making a microfluidic impedance cytometer, especially for the point of care purpose, which should serve the purpose, especially in the rural setting areas. And also the instrument can be used for chemotherapy patient who are undergoing drug treatment. So basically the instrument consists of three parts. The one is the sensor, second is the reader, and the third is the cartridge where all the sample preparation will take place. So the specification of our whole device is that the point of care device is less than 5 kg, and all the sample preparation will take place inside a microfluidic cartridge, which is one-time use only. So basically, you must have heard of Coulter counter principle, where people used to detect the number of cells by counting the number of events. While in our case, we have developed a sensor, a very small sensor, which is like 10 mm cross 10 mm, and which can count the particles even less than 3 micron. It can go up to 2 micron. And the basic principle behind this technology is that whenever a cell crosses between two electrodes, there will be a distortion in the electric field, because of which you will see a change in the current. And based on this current, you can tell what is the size of the particle. And because since you are able to tell the size of the particle, so you can also differentiate what kind of cells, it's in the blood. So basically, when a cell crosses between these two electrodes, you sense number of events. And the number of events is nothing but it just like denotes how many number of cells are crossing between the two electrodes. So basic principle behind this blood cell counting is that since our blood is contains 5 into 10 power 6 erythrocytes, which is RBC, and 5 into 10 power 3 leukocytes, which is WBC, and thrombocytes, nothing but platelet. So in order to ensure that a single cell passes between the two electrodes, you need to dilute the red blood cells 10 to the power 4 times to ensure that only a single event takes place between the two electrodes. And for WBC, since the red blood cells are much more in the blood, so you have to lyse the red blood cells before you go for leukocyte counts. So what happens generally in normal procedure, people count red blood cells separately and leukocytes separately, because you can't have multiple events. So, but while in the case of imaging, so in some cases also people count the cells based on the image. In that case, also of course you can go for single counting system. But since it's a electrode system, so you need to have a good automatic system for sample preparation. So how the system looks, basically, it has a microfluidic, and on the top of the channel there is a electrode fabricated. And between the two fabricated electrodes, when the cell crosses between those electrodes, you see a signal. However, the problem with this kind of technology is that some of the cross current flows between the top plate and the ground plate, because of which the magnitude of the current is dependent on the position of the particle. So we have developed our own system where the position dependency of particle is much more minimized. So what we have right now, you can see a 5-pair of electrode system in which 2 are the measurement electrodes and rest of the 3 plates are ground plates. So what happens in this one, when a cell crosses between the plates, that position dependency of the current is much more reduced. And based on the based on the signal, you can exactly specify what kind of size the cell has. So, another advantage with this kind of system is that you does not need a sheet flow where you require one sheet fluid to squeeze the middle sample in order to increase the sensitivity of the system. But in our case, since the particle, the strength of the magnitude is not dependent on the position, so you doesn't need cell focusing. So because of which, even if the cell is in between of electrode at any position, you can tell what type of cells is that. And also, at the same time, you can apply multiple frequencies on the top plate to have cell signature at many different frequencies. So based on this 2 frequencies, you can exactly identify what kind of cells it's crossing between the top plates. So basically, in order to ensure that our system works, what we did, we have 3 different kind of particle size. One is 3 micron, 5 micron, and the 4 micron particle. What we find that when you plot a histogram, because of the impedance signature, you see a completely 3 kind of different histogram, and based on it, you can exactly tell what is the size of the cell. So, as you can see in the data, 3, 4, and 5 micron particle, their CV is reported. It's 6, 3.3, and 3.5, which also proves that irrespective of where the cell lies in the microfluidics, you always get a same signal. And these are some of the results where the leukocytes, for the leukocyte analysis, we have to lyse the red blood cells. And after lysing, you see there are 3 different kind of cell population, which are clearly, you can see in the cluster graph. One is the lymphocytes, other is the neutrophil and monocytes. So basically, lymphocytes and neutrophil, they can be differentiated based on their size, and the monocytes can be differentiated at high frequency. So you can differentiate neutrophil and the monocytes. So we have a basically histogram plot for the leukocytes, and the down graph shows opacity, which is nothing but ratio of the impedance at high frequency to low frequency. And based on this data, you can exactly identify what kind of cells it is. So thank you. Any question?
So any questions for the presenter? Okay, thank you, Usman. So we have the next paper, blood viscosity based heart disease risk prediction model in edge/fog computing from VIT University, Lata R.
Good afternoon, everyone. I am Lata from VIT Chennai. I am dealing on blood viscosity based heart disease risk prediction. This is my outline of the project. So what is my motivation is higher blood viscosity leads to several problems because heart has to pump thick blood. Blood viscosity means the viscosity of the blood is thick, means the heart cannot pump the blood very quickly. So by detecting that viscosityness of the blood, we can find whether the risk of heart disease is present or not. So if blood is thicker, organs and tissues will get very less oxygen. So the blood vessels will be damaged because of the high friction. So the blood cannot flow throughout the body. So like blood pressure, whenever we are going to a hospital, they are measuring our blood pressure. So like that, if blood viscosity is also measured, whenever we are visiting a hospital, the heart disease can be predicted earlier. And it is related with all risk factors for cardiovascular problem. Recently, a researcher from Harvard University has reported that high viscous blood has a risk of heart attack. So the objectives of this project is to design a heart disease risk prediction model using partially observable Markov decision process, and to depict the model using HiFogSim. HiFogSim is a modeling simulation tool for IoT, fog environments, etc. So this is the proposed method. The viscosity of the blood is predicted through partially observable Markov decision process hierarchical dynamic belief network. We are using a hierarchical dynamic belief network. In that we are going to model a POMDP process. So the decision is aimed at two uncertainty sources. So diagnosis and decision maker are two uncertainty sources. From that the decision is made by the user. So we are using only structure based approximations because it will reduce the complexity of the system. So this is the heart disease risk prediction model. Here we are taking the blood sample and any previous history of the patient. So we are analyzing the blood sample and the history. So while analyzing the blood sample, we are testing is for less viscosity or more viscosity. If the viscosity is less, the patient will become normal, and minimum there will not be any major problem. If the blood viscosity is more, then there is a risk of heart disease in the patient. So in partially observable Markov decision process, we are having three different states. First we have to find what are the states in the model. Then we have to read the observations and then actions. So POMDP is a decision model through which the states, actions and observation, these three are necessary in determining the risk of the heart disease in a patient. So this is determine the best decision based on the blood sample and the past medical history of the patient. So POMDP, what it does is model the past and model the present and predict the future. It is one of the decision making strategy. So we are using HiFogSim to depict the fog layer. So here we are using smart health devices as the bottom layer and fog layer, and for cloud computing we are using this. This fog layer acts as a intermediate layer between the fog devices and the cloud environment. So HiFogSim models IoT and fog environments and measure the impact of resource management techniques in latency, network congestion, energy consumption and cost. So this fog layer extends the cloud services to the edge of the network to decrease the latency and network congestion. So users can define the infrastructure in the fog layer, and whatever latency, resource management techniques can be found using HiFog simulator. So HiFogSim applies sense, process and actuate and distributed data flow model while simulating any application scenario in fog computing environment. And it also includes fog nodes, board for sensor to actuator, these are the fog nodes, and the fog device controls the environment. Then HiFogSim includes nodes, app modules, app edge, app loop and module mapping objects. So this POMDP is simulated in MATLAB, and we are finding whenever there is an increased number of states, what is the readings we are getting, and whenever the time slots are increased, whatever the readings we are getting, we are simulated. So this project is nothing but using a POMDP decision making model, we are analyzing the condition of the patient. So the rewards through independent policies and iterations evaluate the POMDP behavior. The behavior is modeled using the rewards, observations and states of the POMDP model. Then through fog computing, the fog computing is we are using here to depict the simulation model, POMDP model. So these are some of the references.
Any questions? Okay, if there are no questions, let's thank Lata. So the next presentation is technical evaluation of an AI-based secretion and oral hygiene management system for ventilator-associated pneumonia. And the presenter will be Nitesh Kumar Jangir from Koyo Labs.
Good afternoon all. I'm Nitish from Koyo Labs. We are a medical device company based out of Bangalore itself, and then we develop new medical devices in the field of emergency and critical care. One of our device is WebCare, which is world's only intelligent secretions and oral hygiene management system, which can sense and remove secretions from multiple locations of airway, make sure none of these reaches to the lungs and create infection. Same device also pushes antibacterial liquid inside patient's oral cavity. It rinses the whole oral cavity and then make sure that oral hygiene is also maintained automatically. Yeah, I think that's good. So the, in background, the problem of ventilator-associated pneumonia is mostly unknown by most of the people, but this is one of the main reason why deaths happen inside the ICU. Ventilator-associated pneumonia is one of the most common and the most critical hospital-acquired infection, which happens to the patient who are on ventilator. Basically, these patients have a tube going inside their airway. This tube disables their esophagus, so these patients cannot swallow the saliva which we generate. We generate almost around 2 liters of saliva every day, but we swallow all of it. Whenever we, even a drop of it, whenever it tries to get inside our airway, we cough it out. But the patient who are on ventilator, their mechanism of managing saliva or swallowing mechanism has been compromised, so they cannot swallow their saliva automatically, and that's why all these secretions start pooling at multiple places and slowly get inside the lungs and infect them. This is not just a problem we see in India. This is a global issue. Even in US, Europe, Japan, in all countries they have this infection. Just rates are different because of the kind of hygiene they manage and the kind of hygiene and resources we have here. To solve that problem, we developed this device, as I told you, WebCare. It has two parts of it. One part which goes inside the patient's airway, sit inside, is a disposable part, and the other part is our algorithm, and then we have sensors over there which senses presence and absence of these secretions at 3 locations: oral, oropharyngeal, and subglottic, and remove it from all 3 locations based upon timer and sensor data. So the objective of this paper was that to define the process which we have used for our whole verification and validation of this device. Because verification and validation, there are 2 ways how you test medical devices. If your device is on general medical device, then you might be able to find any ISO standard for it and ultimately test it as per that ISO or global harmonized standard available. But then if you are making a new kind of innovative product where the concept itself is totally new, most of the time you have to define your own test criteria. You have to use the statistical methods to figure out what would be the reliability and ultimately define your end goals, and accordingly you design your test. WebCare falls into the second category where we didn't have any standards or any benchmark against which we can test. So we had to design all test protocol, everything by ourselves, and make sure that these matches to the criteria of US FDA and European regulations. So this is some technical information about this product, about that amount, the flow rate, pressures, and sensing which it does, the way it mounts, the way it looks. So this product goes on a pole inside an ICU, and then the first part which you can see is a main device, and then small box you can see, it's a sensor box which contains a light-based sensor to detect sensors. To detect secretions. So a study setup, we have simulated the whole ICU environment in our lab itself, and then we did some statistical analysis to find out that how many, if we are targeting for 3 years of device life, that how many hours we have to run the device. what specific features we have to test more, and what specific feature we can leave without the testing as per the global standard. Yeah. So we have used that Webull and plus Alta software from Reliance Softcorp to test this, and we took through this only we found out that we need to have 3 WebKit devices, and we need to test all of them continuously running for 400 hours. We developed a specific software to test the device, so then device was continuously running. In real operation, device will not be running continuously, it will be running every 30 minutes. But here it was running continuously, so we were able to squeeze number of hours we require for the testing. So if you can, as you can see in table on all 3 units which we have ran, we ran first unit at 199 hours, other one is 186, and then last one is 204 hours. Actually, we exceeded the testing time we needed for it. Yeah. We all 3 units matched our defined criteria, defined pass criteria, which was the amount, the pressure with plus minus 3% we need to test, and then all 3 units shows no sign of degradation for all almost around 600 hours of accumulating testing. So these are some of the references we took for the testing. Wow. To answer any questions.
Questions? Okay, thank you, Nitish. So next we have I mean, pollution has become so much sensitive issue nowadays, and if you go to Delhi, it's hardly to breathe. That's what newspaper report. I don't know how true it is, but I've gone to Delhi many a times. And Bangalore is also kind of approaching Delhi. So next one kind of interesting is an empirical evaluation of COTS air pollution mask in a highly polluted real environment. Highly polluted real environment. That's what we are going to see by Anupama, who was a IIIT Delhi master's student, and now she's working with VMware Bangalore.
Good afternoon, one and all. So I, Anupama, will be presenting an empirical evolution of the COTS air pollution masks in a highly polluted environment. So let me walk you through what I'll be covering. So I'll discuss the motivation, followed by the related work, data collection and methodology, and finally conclude my PPT with the results section. So we know that air pollution has become a real problem, and the particulate matter content has increased by almost like 66% between 2007 to 2010. If we consider the national capital of the country, Delhi, the problem is even worse. So every year we have a Diwali season, post that we have many cases been reported that patients are suffering from respiratory problems and all. So this has become a real issue and it needs to be tackled. So the need of the hour is that people need to be sensitized that what is the quality of air they are actually breathing in. Next line of action is that they need to be made aware of the measures they should take in order to protect themselves from the pollution. So one measure could be using air pollution masks, the respiratory masks. So we have, there are many masks available in the market these days, but the problem is people do not know which mask to go for and how to use them properly in order to achieve the maximum protection from particulate matter. So my research talks about this. So this particular project was carried under the guidance of Professor Mukulika Mathi and Professor Vinayak Nayak. So some work has been done in this field. So Langrish did a study where they took around 16 participants where they were made to walk on a dedicated path with and without a face mask. So they primarily wanted to study the benefits that are achieved on the cardiovascular health when one wears a simple face mask. They considered a 3M mask for their study where they compared it against surgical mask, cyclic mask, etc. But nowhere they have mentioned that how what was the strategy for comparing, what penetration of which particulate matter was considered for their study, and how did they measure the efficacy of the masks. So in our research, we particularly focus on these things. So here are some of the filters that we have considered in our study. So apart from the N-series masks, we have also considered low alternative masks, Honeywell NT-PM 2.5 and the handkerchief. So N-series masks follow the European rating standards. We have considered the low-cost alternatives because it's not affordable to buy expensive masks, so we took the low-cost alternatives as well in our study. So this is how the vendors have advertised. So N99, the nomenclature goes that it should be able to filter at least 99% of the particulate matter. Similar goes for N100 and N95. And Honeywell NT-PM 2.5 is supposed to filter out PM 2.5 dust, haze, bacteria, influenza virus, etc. So you can see that I have listed in the decreasing order of the cost. So N99 mask costs around rupees 1900. That's the expensivest cost that we have considered for our study. And the cheapest one is Honeywell NT-PM 2.5 and a regular handkerchief. So we considered the air with the sensor for our study. So it measures PM 2.5 and PM 10. So you can plug it to a USB cable. It will store the data locally, and as soon as it gets connected to a Wi-Fi, it will send the data to the cloud. And using a mobile app, you can easily download the data. It is calibrated against beta attenuation monitor. That's how it makes sure that the PM values being reported are quite accurate. So we conducted all the experiments in one of the hostels of IIIT Delhi. So we can see in the first image you can see that we took a properly ventilated balcony area to make sure that the sensors and the masks remain exposed to full level of pollution. And the other two images show the setup that has been used in the experiments. I'll walk you through that in my upcoming slides. So let me give you an overview of the experiments conducted. So we have three major agendas. The first experiment was focused on evaluating the performance of masks when used in ideal condition, followed with the experiment where we wanted to evaluate the performance of masks when we used on a human made-up face. And in the last experiment, we wanted to check the durability of masks, at how long should one be using a mask and after how much time should the mask be changed. So the data collection methodology, we wanted to stress test the mask. Stress test means that we wanted to perform all our experiments during that time of the day where the pollution was, where the pollution is at the peak during any time of the day. So what we did, we collected data over 13 days and we did a temporal analysis over that. So we found that between 6 a.m. to 10 a.m., both for PM 2.5 and PM 10, we got the maximum, the PM values recorded were the maximum. So we performed all our experiments during this particular time of the day. So in the first experiment that talks about checking the performance of mask in ideal condition, we considered N95, Honeywell NT-PM 2.5 and a regular handkerchief. So what we did basically was that we cut out a piece of the filter, piece of the fabric from the filter, and we sealed it across the inlet of the air with a sensor. And then we checked that what are the PM 2.5 and PM 10 values being reported by the sensors. So we considered low-cost alternatives because we believe that the expensive and the higher-end ones will perform better than the lower ones, lower-cost masks. So this particular experiment gave insights into how good is the quality of material used in the manufacturing of the mask. In the other experiment, we wanted to compare the performance of mask when a emulated human face wears it. So what we did, we made up a human face. So we used a globe that represents a human face-like curvature. We cut out a piece out of it to make nostrils. Then we made sure that the inlet of the air with the sensor and the nostril remains connected through a cardboard box that has been tightly sealed to ensure that there are no leakages. And the third and the fourth image shows that how we finally fixed that mask over the human made-up face. So in this we considered N95, N99, N100 and handkerchief for the experiments. And once we wrapped the mask around the face, we found out that the fit was not proper and there were many passages that were directly allowing passage of unfiltered air. So we performed another sub-experiment where what we did, we took a N95 mask and we blocked all the openings that we could see due to the poor fit with cotton, and then we observed that how the masks are performing. So this gave insights into how important is proper facial fit for proper performance of a mask. In the last experiment, we compared a N99 one-year-old use mask that's been used for like one entire cycle that sees all seasons and all, and a N99 new mask. We compared the performance of the two. So this gave insights into how the performance of the mask degrades when used extensively and continuously over a duration of time. Let's see how the results were. So for the experiment 1, where we wanted to we wanted to evaluate the performance of mask in ideal condition, we can see that N95 and Honeywell NT-PM 2.5 performed exceedingly well as the normalized PM values remain close to 0. That means they are able to filter out most of the particulate matter. Handkerchief also did a good job, not that well as that of this, but it did a fairly good job. In experiment 2, we find that where we wrap the mask around the human face, we can see that N95 performed the best, followed by N100, followed by a handkerchief, and to our surprise, N99 performed the least, which is the expensivest mask we have considered for our study. So the reason being that the fit for the N99 mask was the poorest among all the filters we have considered. Handkerchief performed well because handkerchiefs are flexible and you can easily wrap it around the face. So it performed better than N99 mask. So proper facial fit does matter for the effective performance of mask. So when we used a cotton padding, we see that the performance significantly improved as when all the air passages were blocked. This again confirms the fact that proper facial fit is important. In the last experiment where we compared a N99 one-year-old mask and a new mask, we can see the performance remains almost the same, which again confirms the fact that the manufacturing quality of this mask is really good. It just depends how you are using. To conclude my presentation, material used is really good. Proper facial fit is the factor. A handkerchief can even perform better than a 2,000 rupees or a 3,000 rupees mask. It can perform better than that. And the durability of these masks is really good. So when you go out, make sure you're wearing it properly. Thank you.
So questions? Okay, thanks Anupama. So next we have Prima, a device for minimally invasive breast cancer surgery by Shruti from BMS College.
Searching for command. How do you use Alt
This one? I'm on this one. Yeah.
Okay. Good afternoon, everyone. I'm Shruti, and I'm from BMS College of Engineering. And our paper title is titled Prima, a device for minimally invasive breast cancer surgery. This is more of an idea. Let me just give you a little backdrop of how we got this idea. We had a course in our 6th semester of engineering, medical device development, handled by Abhishek sir. This is a very dynamic course, so we went a little beyond classroom teaching, and we had a lot of workshops and assignments which made us look very much beyond the textbook. Also, we didn't have a textbook for this subject. And this gave us an idea to start something. It gave us an idea to form an idea, to get an idea. We had a lot of discussions of what device we must take, or we chose a few devices. We said no to a few devices, and then we just couldn't come to a common point. So what did we do? We came up with our own device. Now, how did we get to that point? We were very fascinated by the robotic Da Vinci Xi machine. I'm not sure how many of you are familiar with it, but that's a surgical machine. And that was something very fascinating to all three of us. So what we did, we took that, and we're also very interested in women welfare. So we took something to do with women, breast cancer, and put it together. And I will show you what Prima is in our next slides. Okay, so why do we need this device? Firstly, cancer is one of the oldest diseases ever described by medicine. Of all types of cancer, lung cancer has its highest incidence rate according to a recent report by the WHO. Now in women, it's breast cancer. Now as you can see in the map there, all the pink spots that you can see there indicate breast cancer. So you can see literally the whole world is affected by, all the women in the world are affected by this. Now why minimally invasive surgery? Now these kind of procedures are very, very famous among specialists, patients, insurance organizations. Now what are the advantages of this? Cuts are minimal, extent of contamination is much less, the time spent in clinics, post-operative cares, faster recovery time are its further added advantages. Now when we started doing this, what did we search for? Where did we search for? How did we come to this point? We searched on electronic databases like PubMed, IEEE, ResearchGate, and we searched for keywords like cancer, breast cancer, ultrasound scanning, robotic surgery, safety, usability, and so many more keywords. Now this is Prima. It consists of a robotic surgical machine. If you can see those 4 robotic arms of the machine, it's integrated with a breast scanner and a therapeutic ultrasound equipment to perform the procedure. Now, what is the specification behind the device? So the robotic equipment has 4 arms. The first arm will consist of a breast scanner. The second will consist of the focused ultrasound therapy unit. Third will be to fix a target. The fourth arm, we haven't found any use for it, so as of now, it's just there. And we have a patient table where the patient lies down, and we have further added machines like the anesthesia, display, the CPU console, 3D viewer for the surgeon to operate on, and power source to power all these other devices. Now we also have come up with high-level designs for each of these, the breast scanner unit, image processing, and focused ultrasound therapy based on previous models and designs. Now the device is done. Once it's out in the field, how is it going to work? We have a clinical workflow that we have come up with, we've drawn. Before every procedure, you test and sterilize the instrument. You scan the breast. The detection of tumor is done by the first arm of the machine. Once you have detected it, on the screen, the surgeon or any paramedic or anybody there on the screen can look at the details, size, and the population of the cancer. So after that's done, the other 2 arms, the ultrasound therapy arm and the target arm, are fixed on the patient, whatever the algorithm suggests it to do. After which you detect it, you have to feed the kind of intensity of ultrasound that needs to be given to this patient. You set the intensity and you perform the procedure. You complete the surgery, re-sterilize, and pack it back. Now it's out in the field, procedure also is done. What is its main function? It first needs to identify the presence of lump around the breast region and accurately detect it. How safe is this device? The intensity every time is fixed by the doctor and it's always verified. You have an option of getting an automated or a manual setup. This procedure is non-invasive. The target-specific surrounding cells are not harmed at all. The complete elimination of cancer cells is observed in this procedure. Who can use this? Doctors, nurses, paramedics, anybody familiar as of now with the Da Vinci machine. Else, you learn and you use it. User interface, the console, there are a lot of display screens. A lot of people can view this procedure from multiple locations. How is this machine adaptable? This method of diagnosis you can always use to treat other kinds of cancer too. Next. Okay. This was not how it's supposed to look like. I don't know how this happened. Anyway, designed for serviceability. Now that our machine is out in the system, out in the clinical field, what are we going to do to make sure it works well? What are the steps that we're going to take through the development process to make sure it doesn't fail in the field itself? So first is we're going to use a modular design approach, which includes easy disassembly, simplicity and fewer parts, easily available and interchangeable parts, and plug-in connectors. Now that we know the machine is running, what can go wrong with it? We try to predict what kind of damage can happen. You try to prevent that damage. Okay, you try to prevent the damage. We do this by applying failure mode effect analysis, and after which we use simplification for inspection procedures. Every time we try to see what can be done differently to make this simpler to use. Easy disassembly, adjustment and service points, damage localization, user-friendly installation. Okay. So what can go wrong with our device? Once it's out there, we can have different kinds of failure modes. I don't know where the third one went. corrosion, electrical short or open, or extra excessive torque. Now, how can this happen? Potential causes for these kinds of failures: improper torque, improper operating conditions, erroneous algorithm. The computer gets a brain of its own and it feeds some other intensity and those kind of algorithms, improper alignment, and excessive loading. What are these effects of the failure? Firstly, injury to the patient, inoperability of the product, noise, and degraded performance. Now, how do we classify our device? According to the de novo approach, we have classified Prima as a class 3 device because it involves a lot of risk. If the device malfunctions, you literally have a life lying on your table. Next. We have pulled up a small risk assessment chart, and our score has come to 16, which means that we need to service this product twice a year. And can this device be really made into reality? Well, one of the reviews that we got when we put forth our paper was, this is a very expensive procedure. It's a huge thing. It's a huge thing. So yes, there's definite significant time in production. It's not like I start today and 6 months later my device is out in the market. Approval, clinical trials, manufacturing cost, and servicing cost are pretty high. Mostly, the cost of the procedure itself is very high. Okay. No, that's okay. Okay. So in conclusion, we have understood breast cancer as one of the most leading top cancer female-related mortality deaths. As you can see, from 3500 BC to 2016, there have been significant improvements. From then, you've identified the presence of breast cancer, you've looked through why breast cancer, risk factors of breast cancer, radiotherapy, and so on. So this device that we have proposed introduces a minimally invasive technique to treat cancer, breast cancer. To help this, we propose an amalgamation between 3 devices, as we said: a robotic machine, a breast scanner, and a therapeutic modality. We'd like to see Prima on the timeline just next to that. Thank you. Also, I'd like to leave you all with a quote: for most of medicine, the future is highly uncertain. So hopefully this one day will be future. Thank you. Thank you.
So questions for the team here? Okay, thanks Shruti and team. So we have one more keynote talk in the afternoon where by Dr. Geeta Manjunath, who is having a device which will do. So they're talking about post-diagnosis to diagnose itself non-invasively breast cancer. So she has a device which probably she'll talk about it in our talk. So next we have personalized emotion recognition utilizing speech signal and linguistic cues by Ramya from BMS College.
Very good afternoon to one and all. So emotion recognition, I wish I had my system to recognize my emotions currently, whether I'm nervous or happy. Okay, I would like to mention my guide who has guided me, Dr. Mahabaleshwar Rambhat, who has supported me in this project. And this is the plan for a 10 minutes session. And so we know that mood, emotion, and sentiment being an effective term collectively called as an affective phenomena. So currently out of these, I'll be concentrating more on emotions because momentarily what a person would respond or react to a situation is the main criteria here. So we know that being a most evolved species and all the technology coming up, we try to mimic the biosystems or the thought process, be it in artificial intelligence, machine learning, in many other systems. So here is a list of a very few how humans and machines can perceive alternatively. Auditory, if it is in humans, we know in machines it will be speech analysis and processing, visual, olfactory, somatic, so and various other perceptions that we have. So when it comes to human-computer interaction and making this emotion recognition as the part of HCI, so this will be the very basic how it would look. You talk to the system and it replies back to you, analyzing or giving a measure of your emotion. But what I am presenting is very basic on how speech is actually converting it into text, and I'm classifying it into basic 4 emotions. So applications can be education system wherein the distant education, the tutor can know how the student is actually reacting to his tutorials. Customer support in call centers, we already know how they handle it. The angry customer gets the best service person to handle it. And driver assistance systems, which is a very hot topic, and assistive devices for elderly care or child care or any other applications. So how the idea got originated was a couple of discussion with psychologists, and they told that if a person wants to contact them, he would obviously hesitate to go to the psychologist because he doesn't want to say that initially he has a problem, he has something or the other. So they told if we have an interface, this is actually, we discussed this one, so if an interface can facilitate how well a person is able to, if he actually needs a treatment or set of questionnaire, or how he wants to discuss with psychology, if it really required or not. And then a couple of literature support that I got that in cognitive behavioral therapy, and how such human recognition systems, emotion recognition systems can help in building the assistive devices. So based on all this, this looks a very higher level, product level, but I have done a basic of how actually I'm taking the speech signals, converting it to text and classifying it to emotions. So yeah, this is the basic idea. I'm taking speech signals, and then we wanted open source software, and should be mobile. Currently it is not a mobile, but it should be in a mobile device. So it should be able to support a large vocabulary to understand, to take the information from the speaker. And it is a speaker dependent system right now, and memory efficiency. And on the text classifier, I am telling only for 4 emotions, that is happy, anger, sad, and fear. So this is the elaborated block schematic wherein I'll be explaining it into 2 contexts. One is the speech to text, and then further the text classification. So for this, my basis is ISEAR database, which is a database of different emotions being captured. They have quoted saying emotions induced in lab are often inefficient due to exhibition of diffused emotional features. So what they have done is they have prepared a set of questionnaire wherein it goes back to the person's memory and how he actually felt when something happy happened or something sad happened, etc. So based on this, there are a few questionnaires and interactions and collection of answers that is being. So this is only the text what I have, but what I have done is recordings of so many speech samples, around 400 speech samples I have taken. I have recorded them and fed into my speech recognition system and seen how well it got recognized, and further how well it got classified with the text. So these are my friends who helped me in doing this project. As I go further, I'll explain. So first is the speech recognition system. I used Pocket Sphinx. It's an open source speech recognizer built by Carnegie Mellon University, and then it has specific audio formats. It takes audio in 16 kilohertz, mono and wave format. So basically they are giving acoustic model, language model, and the dictionary. So the tuning of these parameters will give me a stepwise better accuracy. So I tried different combinations. So adapted model, so it is obvious, but adapted model and the dictionary that has information of the general English sentences, etc., will be there, and that gave the highest accuracy. So IICAR, this is the recording part, 1 hour recording. So I prepared 2 set of recordings to adapt the recordings to the model, acoustic model. And I took one more database which I created myself, which had around 100 sentences, so that I wanted to know how well it behaves with the model, acoustic model that we have created. So the word error rate is a measure of the accuracy. So now that I have my set of recordings, I want text analysis. I am feeding it to the speech recognizer. It is given me some output, and how do I go about it? So I used few machine learning algorithms, out of which the linear support vector machines was the best what I got. So I continued analyzing in that, and I used various other, but in linear SVC we got more mean accuracy of classification. So first the sanctity of the data and how equally or well distributed has to be checked, and the k-fold cross-validation was used. So what basically it does is it decides, it splits it into 2 different number of percentages. So if I take the first 5 sentences, the next 2 sentences will be my test. So next 5 sentences, the next 2 sentences will be my test database. So training and testing, training and testing. So it gives the basic sanctity of how well it recognizes. So once my training data is ready, I am going to test it. So I'll directly jump into the results. So on the speech recognizer side, I got a good accuracy of speech recognition, but since the text data what I had was around 4,000 to 5,000 of lines, it was not enough to train. So I got around 50% of accuracy. So both in combined, I mean the automatic speech recognizer plus the text analysis both combined into the system. So that gave me around 50% and 52. So this is the surprise model database for my trained model, so which again gave around 51% as a combined data. So I can further use neural networks. There's another speech recognizer called CALDI, and other CNN algorithms to improve this. So yeah, more text database, I would have improved the model more. So thank you. Thanks a lot. I would like to thank my peers at Robert Bosch for encouraging me in doing this project.
Just 1 or 2 suggestions. No? So one of my colleague, Dr. Sunil Kumar Kuparapu, he's working on emotion detection. Okay. He's taken a different approach. Oh. If you convert the speech into text, right, the emotion part, no, it's stripped out. No? So he's looking at the parameters of the speech, language independent speaker recognition, and if I'm not wrong, he has already hosted application on Play Store, audio emotions. So just have a look at it.
Yeah, sure.
If you want me to connect to Sunil, I'll connect you.
Definitely. Thank you so much.
Any other questions for Ramya? Okay. Yeah. By the way, I see a lot of students as well as a lot of industry and professors in this room. So make sure we will give you a little longer networking break, lunch break. So make sure you have good time during that. Talk to industry people, students, industry can talk to students and professors also. So the last but one paper before we break for lunch is Smart Automated Health Machine using IoT to improve healthcare in rural areas. So do we have the speaker here from? Okay, apparently they wanted to do it at the end. So we have next paper by Gahan and team. So the paper title is A Portable Color Sensor-Based Urine Analysis System to Detect Chronic Kidney Disease.
Good afternoon. Our topic is portable color sensor-based urine analysis system to detect chronic kidney disease. Participants and our mentors. Chronic kidney disease is a gradual degradation of the kidney, and it consists of 5 stages. In the initial stages, it's completely asymptomatic, and when detected in the asymptomatic stage, it's completely reversible. But symptoms only show up in the later stages, that is 3 to 5. In these stages, the only option is dialysis and transplantation. Hence, it is necessary to detect the disease in its asymptomatic stage. Currently, 17% of the population of India is affected by chronic kidney disease. That amounts to around 224 million Indians suffering from CKD, which is around 1 in 6 people. The negative outcomes include the cardiovascular risk, the mortality, and the cost burden to the family due to dialysis and transplantation. Need statement, an easy to implement cost-effective method to screen a population of asymptomatic kidney disease to prevent cardiovascular events and end-stage renal disease in an outreach camp setting. There are various issues faced in mass screening, such as operational difficulty, cultural stigma, resource constraints, and it is mostly cost ineffective. These issues are compensated using a portable urine analyzer, which consists of color sensor and urine strip, Arduino and Arduino software. A urine strip is a basic diagnostic tool which is used to determine the pathological variations in the patient's urine. The results usually take around few seconds to minutes, sometimes a bit longer. In a patient suffering from CKD, due to deterioration of kidneys, the protein albumin is not completely filtered out by the kidneys. As a result, the kidneys are present in the urine. Thus by detecting the presence of albumin in urine, the chronic kidney disease can be detected. The color change in the strip there's a color change in the strip from yellow to green. This indicates the presence of albumin. This color change is detected by the color sensor TCS3200, which is an indication of protein in the urine sample. A color sensor is it's a system of photodiode and a current to frequency converter. The photodiode converts the light to electricity. This electricity is converted into frequency based on the intensity of incident light. This frequency is fed to the Arduino board. Based on the input frequency and the pre-coded frequency, the final results are obtained. Operational flow. Initially, the patient is given the test strip, and after the contact with the sample, he has to wait for around 60 seconds. After the color change, based on the color change, if the color change is green, he is advised to consult a nephrologist. Otherwise, there's no signs of CKD and this is negative. The proposed system aims to detect CKD in its initial stages. Risks of hypertension, cardiovascular events are reduced. CKD-associated anemia is reduced by early detection. In the future, we aim to modify our system to an IoT-based system, where the verified parameters are transferred to a local cloud-based server through a Wi-Fi module, which is used in conjunction with an Arduino board for easy accessibility with an application. This is helpful to ensure systematic tracking of the disease progress in a patient.
Any questions for Gahan? Okay, so if there are no questions before we close for lunch, a couple of announcements. Today evening we have wine and cheese, and also high tea for people who don't like wine, and also live band music, and a lot of stuffs for you waiting for the evening. So make sure you are here even after the workshop. And I would like to thank our sponsors again, INAXIL, IEEE Humanitarian Technologies Activities Committees, and also Lemonson Foundation, Arogya Seva for sponsoring these workshops. And apparently I get to know that other workshops are running behind, but we are the workshop, we are on time. So because we have like 5 more minutes for lunch, I give it over to Rohan to do something interesting.
Hi, thanks. So for the last year and a half, I've been part of a research project which has been doing an unmet need analysis in India. It's been funded by the Tele-medicine Foundation, which is based in Portland, Oregon. And one of the issues they found was that although there were a lot of people working on medical devices and medical technology, they didn't really understand the unmet need. So you have a lot of devices that either made it to a prototype stage and couldn't make it further, or it passed all the regulatory hurdles, it reached the stage where it could be deployed in a clinical setting or reach the market, and it never made it any further than that. So one of the big complaints that a lot of doctors and administrators from hospitals have is that a lot of the devices that come to them aren't really solving a legitimate clinical need. So an exercise that the Tele-medicine Foundation decided to do was to create a database of unmet needs in specific therapy areas. So for the last 18 months, my team and I, which is a team of doctors, engineers, designers, product designers, scientists with PhDs, have spent almost 6 months in clinical settings. We've covered over 40 healthcare centers, primary, secondary, and tertiary, across 9 states in India. And we've, based on our observations and further filtering using the Stanford biodesign process, we've created this database of unmet clinical needs. Now, in most settings, people would want to sell this database, but because it's funded by a foundation, it's completely open source. What we do want to do is to try and disseminate it and get it out to as many people as we can. So we've just finished the research about a month ago, and we've been publishing it in journals. But one of the things we thought we'd do was turn it into a book. And I'm very happy to announce that we're going to be handing that book out to everyone here today. I'll also be sharing the link to our website where you can get the detailed needs specification documents for each of those unmet needs. And most of you here already know me, but my colleague Darian Rodriguez is also there, and we're more than happy to connect with you in case you'd like to take these unmet clinical needs further. On that note, I think I'm going to close because I'm keeping you all from lunch. But I'd like to take on what Abhishek said and extend my thanks to everyone who came out to NetHealth. Not just the speakers, but also everyone who presented their papers, as well as the other delegates here. And NetHealth really wouldn't have been the same without all of you here. As Abhishek said, please stay until the evening. We have cocktails and a live band performing. And it's, of course, open to everyone. Lunch is now served, so I'll leave you all to it. We're going to be back at 2, where we're going to have more keynote sessions on 3D printing, on nanotechnology, on tele-ICUs and tele-monitoring as well. So there's a lot in store. Thank you.
So while exiting, you have a goodie, that is Rohan's book, which makes a lot of our life easier, being professor at least. Yeah, thank you.
Fetch my power.